For thousands of years, humanity has gazed upward and wondered what lies beyond our tiny corner of space. We've sent robots to Mars, landed on the Moon, and flung spacecraft past the edge of our planetary neighborhood. But here's the question that keeps scientists awake at night. Will we ever truly leave our solar system? Will humans ever set foot on a world orbiting another star? We will discover today. Now let's begin. Imagine standing on Earth and looking toward the nearest star system, Alpha Centauri. It's roughly 25 trillion miles away. That's 4.3 light-years in astronomical terms. A light-year is the distance light travels in 1 year, moving at about 186,000 miles per second. Think about that for a moment. Light, the fastest thing in the universe, takes over 4 years to reach Alpha Centauri from Earth. Now consider this. Our fastest human-made object, the Parker Solar Probe, travels at speeds approaching 430,000 miles per hour when it whips around the Sun. That sounds incredibly fast, right? At that speed, you could circle Earth in less than 6 minutes. But here's the humbling truth. Even at that breakneck velocity, it would take the Parker Solar Probe over 6,000 years to reach Alpha Centauri. 6,000 years. That's longer than all of recorded human history. This is the first massive obstacle we face when we talk about leaving our solar system. The universe is incomprehensibly vast, and our current technology makes us look like ants trying to cross an ocean. But don't lose hope yet, because humanity has a history of doing the impossible. Let's talk about what we've already achieved. Right now, as you watch this video, 5 spacecraft built by human hands are heading into interstellar space. Voyager 1 and Voyager 2, launched back in 1977, have already crossed the boundary where the Sun's influence fades and true interstellar space begins. They're our first ambassadors to the galaxy, carrying golden records with sounds and images from Earth, messages in a bottle tossed into the cosmic ocean. Pioneer 10 and Pioneer 11, launched in the early 1970s, are also drifting outward, though we've lost contact with them. And New Horizons, the spacecraft that gave us those stunning images of Pluto in 2015, is speeding toward the edge of our solar system as well. These robotic explorers are incredible achievements. They prove we can send objects beyond our Sun's gravitational grip. But there's a catch. These spacecraft are coasting, not accelerating. They're moving at speeds between 30,000 and 40,000 miles per hour. At those velocities, they'll take tens of thousands of years to reach even the nearest stars. Voyager 1, our most distant spacecraft, won't come anywhere close to another star for about 40,000 years. So we've left the solar system, technically speaking, but we haven't left it in any meaningful way. Our machines are barely crawling through the vast desert of interstellar space. If we want to reach other stars within a human lifetime, we need something radically different. We need propulsion systems that sound like science fiction. Enter one of the most exciting projects in modern space exploration, Breakthrough Starshot. Announced in 2016 by physicist Stephen Hawking and billionaire investor Yuri Milner, this ambitious initiative aims to send tiny spacecraft to Alpha Centauri within our lifetimes. The concept is both elegant and wild. Instead of building massive rockets, Breakthrough Starshot proposes using thousands of tiny probes, each no bigger than a microchip, attached to ultra-thin light sails. Here's how it works. Powerful lasers on Earth would beam intense light at these sails, pushing them the way wind pushes a sailboat. But instead of wind, we're using photons, particles of light. The force is small, but because the probes weigh almost nothing, they could accelerate to 20% the speed of light. That's about 134 million miles per hour. At that velocity, these tiny explorers could reach Alpha Centauri in just 20 years. 20 years? Not 6,000, not 40,000, 20. If you're feeling amazed right now, hit that subscribe button and give this video a thumbs up. we're just getting started. And trust me, the journey ahead gets even more fascinating. Your support helps me bring more cosmic mysteries to life. Now, before you get too excited, let's acknowledge the elephant in the room. Breakthrough Starshot faces enormous technical challenges. Building lasers powerful enough to push these sails requires technology we haven't perfected yet. We're talking about laser arrays that would need to generate about 100 gigawatts of power, roughly the output of 100 nuclear power plants, all focused on a tiny sail moving at incredible speeds. Then there's the challenge of the sail itself. It needs to be impossibly thin, lighter than a butterfly's wing, yet strong enough to withstand the intense heat and pressure from the laser beam. Scientists are experimenting with materials just a few atoms thick, but manufacturing them at scale is a whole different ballgame. And even if we solve those problems, there's another hurdle: communication. These tiny probes would be so small they couldn't carry large antennas or powerful transmitters. Sending data back across 4 light-years of space would be like trying to shout from New York to London and expecting someone to hear you clearly. Engineers are working on ways to use the sails themselves as reflectors, bouncing laser signals back to Earth, but this technology is still in its infancy. Yet despite these challenges, Breakthrough Starshot represents something profound. It shows that interstellar travel isn't just a fantasy for future civilizations. It's something we could potentially achieve this century with enough resources, innovation, and determination. The project is currently in its research phase, with scientists around the world testing materials, refining designs, and tackling the physics one problem at a time. But let's zoom out for a moment. Why are we even talking about leaving our solar system? What's driving this urge to reach for the stars? Part of it is pure curiosity, that deeply human need to explore and discover. But there's more to it than that. In the past 3 decades, astronomers have discovered over 5,000 planets orbiting other stars. These exoplanets come in astonishing variety: gas giants larger than Jupiter, rocky worlds scorched by their parent stars, ice giants in the outer reaches of distant solar systems, and most exciting of all, planets in the habitable zone, the region around a star where liquid water could exist on a planet's surface. Some of these worlds are tantalizing. Take Proxima Centauri b, a planet orbiting the closest star to our Sun, Proxima Centauri, which is part of the Alpha Centauri system. Discovered in 2016, this planet sits right in the habitable zone. It's roughly Earth-sized, and scientists estimate its surface temperature could support liquid water. Could there be oceans on Proxima Centauri b? Could there be life? We don't know yet. Our telescopes can detect these planets and measure some of their properties, but we can't see them in enough detail to answer the big questions. That's why actually going there matters. Pictures from orbit, measurements from atmosphere-sniffing instruments, maybe even rovers exploring alien landscapes. These would revolutionize our understanding of life in the universe. The James Webb Space Telescope, launched in 2021, is already giving us incredible insights into exoplanet atmospheres. It can analyze the light filtering through a planet's atmosphere as it passes in front of its star, revealing the chemical fingerprints of gases like water vapor, methane, and carbon dioxide. These observations are teaching us which planets might be worth visiting, narrowing down our target list for future interstellar missions. But here's where things get really interesting. What if we're not just looking for planets to study? What if we're looking for backup plans? Earth has been our home for hundreds of thousands of years, but it won't last forever. In about 5 billion years, our Sun will expand into a red giant, swallowing Mercury, Venus, and possibly Earth itself. Long before that, the Sun will gradually brighten, making Earth uninhabitable in perhaps 1 billion years. That might sound like a comfortable cushion of time, but there are more immediate threats: asteroid impacts, supervolcanic eruptions, climate change, nuclear war, the list of potential catastrophes is sobering. Some scientists argue that becoming a multi-planet species isn't just about exploration, it's about survival. If humanity wants to endure for millions of years, we'll eventually need to spread beyond Earth, beyond Mars, beyond our solar system entirely. This brings us to a fundamental question. What kind of interstellar mission could we actually pull off? There are roughly 3 categories, each with wildly different timelines and challenges. First, there are flyby missions like Breakthrough Starshot. These are the simplest in concept. You accelerate a probe to enormous speeds, it zips past the target star system, gathers data for a few hours or days, and sends the information back home. The advantage is speed and simplicity. The disadvantage is that you get only a brief snapshot, a cosmic drive-by that can't stop to investigate anything closely. Second, there are orbiter missions. These would slow down enough to enter orbit around a target star or planet, allowing months or years of detailed study. But here's the problem. Slowing down requires almost as much energy as speeding up. If you accelerate a spacecraft to 20% light speed, you need a massive amount of energy to decelerate it at the destination. Without a convenient laser array at Alpha Centauri to help you brake, you'd need to carry your own fuel, which makes the spacecraft heavier, which requires more energy to accelerate in the first place. It's a vicious cycle that quickly makes the mission impractical with current technology. Third, and most ambitious, are crewed missions. Sending humans to another star system is orders of magnitude harder than sending robots. Humans need food, water, air, radiation shielding, and living space. They need protection from cosmic rays, high-energy particles that could damage DNA and cause cancer on a multi-decade journey through interstellar space. They need artificial gravity or exercise regimens to prevent muscle and bone loss. And they need psychological support to handle the isolation and confinement of a voyage that could last generations. This leads to one of the most fascinating concepts in interstellar travel, the generation ship. Imagine a massive spacecraft large enough to sustain a small community of humans for centuries. The original crew who depart Earth would never see the destination, neither would their children or their children's children. Instead, multiple generations would live and die aboard the ship, with only the final generation arriving at the new star system. It sounds like the plot of a science fiction novel, and in many ways it is. But scientists have seriously studied the concept. How big would a generation ship need to be? What kind of society would develop in such an isolated environment? How would you maintain technology and knowledge across centuries? These aren't just engineering questions, they're anthropological, psychological, and ethical puzzles. Some researchers estimate you'd need a population of at least several thousand people to maintain genetic diversity and prevent inbreeding over multiple generations. You'd need robust ecosystems to recycle air, water, and waste. You'd need power sources that could function for hundreds of years, perhaps nuclear fusion reactors or enormous solar arrays. And you'd need a way to keep the crew motivated and hopeful, generation after generation, as they journey through the dark void between stars. The challenges are staggering, but let's not forget, humans have undertaken seemingly impossible journeys before. When the Polynesians set out across the Pacific Ocean in outrigger canoes over 1,000 years ago, they embarked on voyages spanning thousands of miles, discovering islands scattered across an ocean larger than all the continents combined. They had no maps, no GPS, no weather satellites. They navigated by stars, wave patterns, and an intimate understanding of nature. Many didn't survive, but those who did changed the world. Interstellar travel would be the next great migration, a journey that makes crossing the Pacific look like a stroll around the block. But the human spirit that drove those ancient explorers still burns within us. We're a species that looks at the impossible and asks, how can we make it possible? Now let's talk about propulsion. because this is where the rubber meets the road, or rather, where the spacecraft meets the vacuum of space. We've already discussed light sails and lasers, but there are other wild ideas on the table. One concept is nuclear pulse propulsion, specifically Project Orion, an idea that originated in the 1950s. The concept is beautifully insane. You detonate nuclear bombs behind your spacecraft, and the shockwaves push you forward. Each explosion provides a massive kick, accelerating the ship incrementally. A large spacecraft using this method could theoretically reach a few % of light speed. The United States actually studied this seriously during the Cold War. Engineers calculated that it could work, at least in theory. The spacecraft would need a huge shock-absorbing pusher plate to handle the repeated nuclear blasts, but the physics checked out. The project was shelved, partly due to the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear explosions in space. But the concept hasn't disappeared. Some modern scientists have revisited it, wondering if controlled fusion explosions could provide a cleaner, more acceptable version of the same idea. Another approach is antimatter propulsion. When matter and antimatter meet, they annihilate each other in a burst of pure energy, converting mass directly into energy according to Einstein's famous equation, E equals mc². This makes antimatter the most energy-dense fuel imaginable. A single gram of antimatter reacting with a gram of matter would release energy equivalent to a nuclear bomb. The problem? We can barely produce antimatter, and storing it is incredibly difficult. At CERN, the European Organization for Nuclear Research, scientists have managed to create and trap tiny amounts of antimatter. We're talking about a few atoms at a time. Producing even a single gram would require technology far beyond our current capabilities and energy expenditures that would bankrupt nations. But if we could solve the production and storage problems, antimatter rockets could potentially reach significant fractions of light speed, making interstellar travel feasible within a human lifetime. Then there's the Bussard ramjet, a concept proposed by physicist Robert Bussard in 1960. Imagine a spacecraft with an enormous magnetic scoop at the front, thousands of miles wide. As the ship moves through space, the scoop gathers hydrogen atoms from the interstellar medium, the incredibly thin gas that exists between stars. The collected hydrogen gets funneled into a fusion reactor, which powers the ship and provides continuous thrust. It's an elegant idea. Your spacecraft gathers fuel as it goes, like a car that could run forever by scooping up air. The challenge is that interstellar space is astonishingly empty. There's roughly 1 hydrogen atom per cubic centimeter out there. That's a better vacuum than anything we can create in laboratories on Earth. Your scoop would need to be truly enormous to gather enough material to make fusion practical, and the drag from the magnetic field itself might slow you down more than the thrust pushes you forward. Still, variations of this concept continue to intrigue physicists. Now let's venture into more speculative territory. What about warp drives? If you've watched Star Trek, you've seen the Enterprise jump to warp speed, bending space itself to travel faster than light without actually moving faster than light. Sounds like pure fantasy, right? Well, maybe not entirely. In 1994, physicist Miguel Alcubierre proposed a mathematical solution to Einstein's field equations that describes a warp bubble. The idea is that you contract space in front of your spacecraft and expand it behind you, creating a wave of curved spacetime that carries your ship along. Inside the bubble, you're in flat space, not moving faster than light relative to your immediate surroundings, but the bubble itself moves through space, potentially at superluminal speeds. Before you get too excited, there are massive caveats. The original Alcubierre drive required exotic matter with negative energy density, something we've never observed and may not exist. The energy requirements were absurd, equivalent to the mass energy of entire planets. Subsequent refinements by physicists like Harold White at NASA have explored whether more reasonable energy requirements might be possible, perhaps reducing the needed energy to something closer to the mass of a large spacecraft. But we're still talking about physics that's firmly in the theoretical realm, with no clear path to practical implementation. And even if we could build a warp drive, there are other problems. How do you steer it? How do you turn it off safely? What happens to anything in the path of your warp bubble? Some calculations suggest that when you decelerate, all the particles you've swept up during your journey would be released in a devastating radiation burst that could sterilize your destination. Probably not ideal for making a good first impression on an alien civilization. Another exotic idea is the wormhole, a theoretical tunnel through space-time connecting two distant points. If wormholes exist and can be stabilized, both enormous ifs, you could step through one end and emerge light years away almost instantaneously. Einstein's general relativity allows for wormholes mathematically, but keeping them open would likely require exotic matter, similar to the warp drive problem. And we've never observed a wormhole, so we don't know if they exist in nature or could ever be created artificially. These ideas, warp drives, wormholes, antimatter engines, they push at the boundaries of known physics. They're not impossible in the sense that they violate fundamental laws of nature, but they require technologies and materials that might be centuries or millennia beyond our current abilities. Or they might be forever out of reach, prohibited by aspects of physics we haven't discovered yet. So let's return to more near-term possibilities. What could we actually do in the next 50 to 100 years? Most scientists believe the first interstellar missions will be robotic probes, probably using some variation of light sail technology combined with miniaturization. Think of spacecraft the size of smartphones, packed with sensors, cameras, and communication equipment, accelerated by powerful lasers or possibly nuclear electric propulsion systems. These missions would be reconnaissance, scouting missions to gather basic information about nearby star systems. They'd take images, measure magnetic fields, analyze any planet's atmospheres, and search for radio signals or other signs of technology. The data they send back would help us plan more ambitious missions, perhaps larger probes that could slow down and orbit interesting targets. NASA and other space agencies are already taking baby steps toward interstellar technology. The Parker Solar Probe, which I mentioned earlier, is testing materials and systems in the extreme environment near the Sun, where temperatures exceed 2,000 degrees Fahrenheit. The insights gained from missions like this help engineers understand what spacecraft would face during high-speed interstellar travel. Similarly, the Voyager missions continue to send back data about the boundary between our solar system and interstellar space, revealing unexpected complexities about magnetic fields, plasma densities, and cosmic ray intensities. Every piece of information helps us prepare for the next leap outward. But here's a sobering thought that we need to address. Maybe we won't leave the solar system, at least not in the way we imagine. Maybe the future of humanity in space looks different from Star Trek or Star Wars. Maybe instead of physically traveling to other stars, we'll send our consciousness, our information, our culture. Consider this. By the time we have the technology to build interstellar spacecraft, we might also have advanced artificial intelligence and brain-computer interfaces. Instead of sending fragile biological humans on dangerous multi-generation voyages, we might upload human consciousness into machines that can survive the harsh conditions of space travel. These digital explorers could hibernate during the journey, awakening only when they reach their destination, immune to radiation, not needing food or water or air. It sounds like science fiction, and it is, for now. But researchers in neuroscience and computer science are making progress in understanding how the brain encodes information and how we might interface with machines. Whether true consciousness can be uploaded or replicated remains a profound philosophical and scientific question, but the idea isn't as far-fetched as it might have seemed a few decades ago. Another possibility is that we'll focus on transforming our own solar system before venturing to others. There's an enormous amount of space and resources right here in our cosmic neighborhood. The asteroid belt contains more mineral wealth than has ever been mined on Earth. The moons of Jupiter and Saturn harbor subsurface oceans that could potentially host life. The outer solar system is rich in water ice and organic compounds. Some futurists envision a future where billions of humans live not on planets, but in artificial habitats scattered throughout the solar system, rotating cylinders that create artificial gravity, space stations orbiting asteroids, dome cities on Mars and the Moon. The physicist Gerard K. O'Neill proposed such colonies in the 1970s, and the concept has inspired generations of space enthusiasts. If we built such a civilization spreading across the solar system over the next few centuries, would we still feel the pull to go to other stars? Or would we be content with the vast frontier we've already settled? I think we would still go, because the drive to explore isn't just about resources or living space. It's about something deeper, something woven into the fabric of what makes us human. We explore because we're curious. We explore because there might be answers out there to questions we've been asking since we first looked up at the night sky. Are we alone? How did life begin? What else is possible in this vast universe? Let's talk about that profound question. Are we alone? The search for extraterrestrial intelligence, known as SETI, has been scanning the skies for radio signals from alien civilizations for over 60 years. So far, we've heard nothing definitive. The universe remains mysteriously silent, at least at the frequencies and directions we've been listening. This silence has led to what's called the Fermi paradox, named after physicist Enrico Fermi. The paradox goes like this. Our galaxy contains hundreds of billions of stars, many of them billions of years older than our Sun. If even a tiny fraction developed intelligent life, and if even a small percentage of those civilizations developed interstellar travel, the galaxy should be teeming with evidence of alien activity. So where is everybody? Why haven't we seen signs of megastructures, received radio messages, or been visited by curious aliens? There are many proposed solutions to the Fermi paradox, and they range from hopeful to unsettling. Maybe intelligent life is incredibly rare, and we're among the first civilizations to arise. Maybe life is common, but intelligence is a rare fluke. Maybe civilizations tend to destroy themselves before achieving interstellar travel, a sobering thought given our own challenges with nuclear weapons and climate change. Or maybe interstellar travel is simply too difficult, too expensive, too impractical for any civilization to attempt on a large scale. This is sometimes called the Great Filter, the idea that there's some barrier that prevents civilizations from spreading across the galaxy. The terrifying question is whether that filter is behind us, meaning we've survived challenges that destroyed other civilizations, or ahead of us, waiting to catch us too. But here's another possibility, one that's more hopeful. Maybe civilizations are out there, but they're quiet. Maybe they've learned that broadcasting your presence to the galaxy is dangerous, or maybe they communicate using methods we haven't discovered yet. Perhaps they use tightly focused laser communications instead of omnidirectional radio signals, or quantum entanglement, or some technology we can't even imagine. We might be like someone in the 19th century looking for telegraphs while everyone else is using the internet. If there are other civilizations out there, and if they've solved interstellar travel, what might we learn from them? This is one of the most compelling arguments for attempting to leave our solar system, the possibility of contact, of joining a broader galactic community, of learning from others who've faced the same challenges we're facing now. Imagine receiving a message from a civilization that's survived for 1 million years. What could they teach us about sustainability, about organizing society, about the nature of reality itself? Or imagine landing on a planet in Alpha Centauri and finding ruins, archaeological evidence of a civilization that rose and fell before humans even existed. What would those ruins tell us about the life cycle of intelligent species, about the dangers and opportunities that await us? Even if we find no signs of intelligence, discovering life of any kind beyond Earth would be revolutionary. Finding microbial life on Mars or in the subsurface oceans of Europa or Enceladus would answer one of humanity's oldest questions. Is life a cosmic accident, unique to Earth, or a natural outcome of chemistry that emerges wherever conditions are right? If we find that life arose independently multiple times just in our own solar system, that would suggest the universe is abundant with life, and if life is common, then perhaps intelligence is less rare than we fear. Every discovery brings us closer to understanding our place in the cosmic story. Now let's shift gears and talk about the human element of interstellar exploration. We've discussed the technology, the physics, the engineering challenges, but what about the people who might undertake such a journey? What kind of person volunteers for a one-way trip to another star system, knowing they'll never see Earth again? History offers some clues. Throughout human history, people have left everything behind to journey into the unknown. The Polynesians who sailed across the Pacific, the pioneers who crossed continents in covered wagons, the immigrants who boarded ships to distant lands, knowing they'd likely never return home. These journeys were dangerous, often deadly, and yet people made them anyway, driven by hope for a better life, by curiosity, by desperation, or by a simple inability to resist the call of the horizon. An interstellar journey would be the ultimate voyage of no return. Current technology suggests a trip lasting decades at minimum, more likely centuries. Anyone who departed would be saying goodbye to Earth, to everyone they know, to the accumulated culture and history of humanity. They'd be betting everything on the possibility of something better, something new, something worth the sacrifice. Would enough people volunteer? I suspect they would. Even today, when Mars colonization is discussed, a far more achievable goal than interstellar travel, there's no shortage of people willing to go on a one-way trip to the Red Planet. The human spirit, at least for some people, finds the unknown more appealing than the familiar, but we need to be honest about the psychological challenges. Studies of isolated groups, Antarctic research stations, submarines, space stations, show that even well-trained, carefully selected people struggle with confinement and isolation. They experience depression, anxiety, interpersonal conflicts. The International Space Station, orbiting just 250 miles above Earth, requires careful psychological support for crews staying only 6 months. Now imagine a generation ship, decades or centuries from any other human settlement. The crew couldn't call home for advice. Communication delays would stretch to years as the ship moved farther from Earth. A message saying, "Help, we need assistance," would arrive years after it was sent, and any reply would take years more to return. The crew would be truly, fundamentally alone. This isolation raises fascinating questions about human culture and identity. Would the crew develop their own language, their own customs, their own worldview distinct from Earth? Would they still consider themselves human in the way we understand it, or would they evolve into something new, culturally, if not biologically? And what about the ethics of a generation ship? The first generation chooses to go, but their children don't have a choice. They're born into a spacecraft, confined to a metal world sailing through the void, committed to a mission they didn't volunteer for. Is it ethical to impose that on future generations? Or is it similar to how all children are born into circumstances not of their choosing, and a generation ship is simply a more extreme version of the human condition? These aren't just abstract philosophical questions. If we're serious about interstellar travel, we need to grapple with them. We need to think carefully about the kind of society we'd create on such a vessel, the rights and responsibilities of each generation, the ways we'd preserve knowledge and purpose across centuries. Some researchers have proposed interesting solutions. One idea is the seed ship, a variant of the generation ship concept. Instead of carrying living humans, the ship carries frozen embryos or the genetic information to create humans, along with artificial intelligence or robots to care for and raise the children once the destination is reached. It's a way to avoid the ethical problems of multi-generational confinement while still delivering human biology to another star system. Of course, this raises its own ethical concerns. Who decides what genetic information to include? How do machines raise human children in a way that produces psychologically healthy adults? What culture and values get transmitted? These questions don't have easy answers. Another approach is suspended animation or cryogenic sleep, concepts that appear frequently in science fiction. The idea is that crew members would be frozen or placed in a state of extremely slowed metabolism for the duration of the journey, waking only when they reach their destination. This would sidestep the generation ship problem entirely. The crew who leaves Earth would be the same crew who arrives at Alpha Centauri. Unfortunately, we're nowhere close to this technology. While we can freeze and preserve individual cells, embryos, and even some simple organisms, freezing and reviving a complex mammal without causing fatal damage remains beyond our abilities. Ice crystals form during freezing, rupturing cell membranes. Metabolism doesn't just slow down smoothly, it stops in ways that cause cascading failures in biological systems. Some scientists are researching induced hypothermia and reduced metabolic states inspired by hibernating animals like bears and ground squirrels. These creatures can slow their metabolism dramatically for months without suffering damage. If we could induce a similar state in humans and maintain it safely for years or decades, it might provide a middle ground between conscious travel and full cryogenic suspension. Research in this area is still in early stages, but it's not impossible to imagine breakthroughs in the coming decades. Let's step back and consider the timeline. When might humanity actually attempt its first interstellar journey? Predictions vary wildly, but we can make some educated guesses based on current technological trends and the challenges we've discussed. Robotic flyby missions using light sail technology or advanced nuclear propulsion could potentially be launched within 50 to 100 years, assuming continued investment and no major setbacks. These would be small probes, perhaps thousands of them launched over time, creating a wave of tiny explorers heading toward nearby star systems. More sophisticated missions capable of slowing down and orbiting target stars would require either breakthrough technologies we haven't developed yet, or massive investment in nuclear pulse propulsion or fusion drives. We're probably looking at 100 to 200 years before such missions become feasible, assuming steady technological progress. As for crewed missions, particularly generation ships, we're venturing into the realm of multiple centuries. We'd need not just the propulsion technology, but also closed-loop life support systems, radiation shielding, artificial gravity solutions, and answers to all those psychological and ethical questions we discussed. Most experts who've seriously studied the question suggest we're at least 200 to 500 years away from attempting crewed interstellar voyages. But here's the fascinating part. Technological progress isn't linear, it accelerates. Consider that the Wright brothers flew the first airplane in 1903. Just 66 years later, humans walked on the moon. In the span of a single human lifetime, we went from barely leaving the ground to leaving our planet entirely. Or think about computers. The first electronic computers in the 1940s filled entire rooms and had less computing power than the phone in your pocket. Now we carry supercomputers everywhere, connected to a global network that would have seemed like magic to someone from the mid-20th century. If our technological progress continues to accelerate, and particularly if we develop truly advanced artificial intelligence that can help us solve engineering problems, the timeline for interstellar travel could compress dramatically. Technologies that seem impossible today might become routine in 50 years rather than 500. There's also the possibility of wild cards, unexpected discoveries that change everything. What if we find a way to manipulate gravity directly, leading to propulsion systems we haven't imagined? What if we discover that wormholes do exist naturally and we figure out how to use them? What if we make contact with an alien civilization willing to share their technology? These possibilities might sound far-fetched, but science has a history of surprising us. Quantum mechanics, relativity, the discovery of exoplanets, the acceleration of the universe's expansion, these were all unexpected revelations that reshaped our understanding of reality. We should remain humble about what we think is possible. Now let's consider an important factor that often gets overlooked: motivation. Will humanity maintain the drive to explore space over the coming centuries? Space exploration is expensive. The Breakthrough Starshot initiative has estimated costs in the billions of dollars over decades of development. Crewed interstellar missions would cost exponentially more, potentially trillions of dollars, or the equivalent of entire nations' economies dedicated to the effort over generations. Why would we spend that much? What's the return on investment for interstellar exploration when we have so many problems here on Earth? Poverty, disease, climate change, political instability. It's a legitimate question, and there are several answers. First, space exploration and solving Earth's problems aren't mutually exclusive. The total global spending on space exploration is a tiny fraction of global military spending or economic activity. We can do both. In fact, technologies developed for space exploration often have Earth-bound applications. Solar panels, water purification systems, medical devices, materials science, all have benefited from space research. Second, some challenges like asteroid impacts or the long-term survival of humanity beyond Earth's eventual uninhabitability require space-based solutions. We can't solve those problems by looking only inward. Third, and perhaps most importantly, exploration inspires us. It gives us a sense of shared purpose, a narrative larger than our individual lives. The Apollo program inspired an entire generation to pursue careers in science and engineering. The images from the Hubble Space Telescope and the James Webb Space Telescope fill us with awe and wonder, reminding us that we're part of something magnificent and mysterious. Interstellar exploration, even if we only send robots in our lifetimes, would continue that tradition of inspiration. The first images from a planet orbiting Alpha Centauri would be historic, something humans would remember for as long as our species exists. We'd see landscapes that no human eyes have ever witnessed, skies filled with unfamiliar constellations, perhaps even evidence of life beyond Earth. That brings us to one of the most thrilling aspects of interstellar exploration: the possibility of finding biosignatures, chemical or physical evidence of life. Modern telescopes are beginning to analyze exoplanet atmospheres in detail, looking for combinations of gases that might indicate biological activity. For example, Earth's atmosphere contains oxygen and methane simultaneously, which is unusual because these gases react with each other. The reason both persist is that life constantly replenishes them. Plants produce oxygen through photosynthesis, and various organisms produce methane. If we found a similar atmospheric signature on an exoplanet, it would be strong evidence for life, though not absolute proof. The James Webb Space Telescope and future observatories like the proposed Habitable Exoplanet Observatory could potentially detect biosignatures in the atmospheres of nearby exoplanets within the next few decades. But there's a huge difference between detecting possible signs of life from light years away and actually visiting a planet to confirm it. Imagine sending a probe to a planet where we've detected oxygen and methane. The probe enters orbit, takes high-resolution images, maybe deploys landers to sample the soil and water. It finds microbial mats in shallow seas, or towering fungal structures in alien forests, or crystal formations that grow in patterns suggesting some form of silicon-based life. That discovery would reshape human civilization's understanding of itself. Or imagine a darker scenario. We find clear evidence of past life, fossil remains of complex organisms, but nothing alive. A dead world, once teeming with biology, now silent. What killed it? Climate catastrophe? Asteroid impact? The death of its star? Such a discovery would be both fascinating and sobering, a reminder that life, even once established, isn't guaranteed to persist. These possibilities drive the scientific hunger for interstellar exploration. We're not just curious about what's out there, we're searching for context, for comparison points that help us understand our own existence. Every new world we study teaches us something about Earth, about planetary formation, about the conditions necessary for life, about the ways ecosystems can evolve. But let's be realistic about the challenges ahead. Even if we solve the propulsion problem, even if we build spacecraft capable of reaching other stars, there are hazards in interstellar space that we're only beginning to understand. Cosmic rays are one such danger. These high-energy particles, mostly protons accelerated by supernovae and other violent cosmic events, constantly bombard spacecraft. Earth's magnetic field and atmosphere protect us from most cosmic rays, but a ship in interstellar space has no such protection. Over years or decades of exposure, cosmic rays could damage electronics, degrade materials, and harm biological tissue, increasing cancer risk for any living crew. We'd need robust shielding, perhaps thick layers of water, or hydrogen-rich materials that absorb and scatter the radiation. Some designs propose surrounding the crew quarters with tanks of water, which serves double duty as radiation shielding and life support reserve. Others suggest using magnetic fields to deflect charged particles, creating an artificial magnetosphere around the spacecraft. All of these solutions add weight and complexity. Then there's the danger of collisions. Space isn't completely empty. Interstellar space contains dust grains, tiny particles of rock and ice. At normal speeds, these particles are harmless, but at 20% light speed, a dust grain the size of a snowflake hits with the energy of an exploding hand grenade. Even smaller particles, microscopic specks, become hazardous projectiles. Spacecraft traveling at extreme velocities would need forward shields, possibly thick layers of expendable material or plasma clouds generated by the ship itself to vaporize incoming particles before they strike critical components. Engineers working on Breakthrough Starshot are grappling with this problem right now, trying to design light sails thin enough to accelerate quickly but resilient enough to survive the journey. Navigation presents another challenge. At interstellar distances, even small errors in trajectory result in enormous misses. Imagine aiming for a target 4 light-years away. An error of just 1 degree means you miss your destination by trillions of miles. Spacecraft need incredibly precise navigation systems, probably using pulsars, rapidly rotating neutron stars that emit regular pulses of radio waves as cosmic lighthouses to triangulate position. Communication, as I mentioned earlier, becomes increasingly difficult with distance. Radio signals travel at light speed, so even at Alpha Centauri, there's an 8.6-year round-trip communication delay. Ask a question, wait 4.3 years for the signal to arrive, wait another 4.3 years for the response. By the time you get an answer, the situation has likely changed dramatically. This delay means that interstellar spacecraft must be largely autonomous, capable of making decisions without waiting for instructions from Earth. Advanced artificial intelligence would be essential, something that can diagnose problems, make repairs, adjust course, and make scientific observations without constant human oversight. Interestingly, this need for autonomous spacecraft might solve itself as we develop AI for purposes here on Earth. The same technologies that enable self-driving cars, medical diagnosis systems, and scientific research assistants could be adapted for space exploration. By the time we're ready to send interstellar probes, we might have AI sophisticated enough to serve as the mission's decision-making brain. Let's talk about something that might seem mundane, but is actually crucial: power. How do you keep a spacecraft running for decades or centuries in the cold darkness between stars? Solar panels won't work. Sunlight fades rapidly as you leave the solar system, becoming useless beyond the orbit of Jupiter. You need a power source that's compact, long-lasting, and reliable. Current deep space missions like Voyager and New Horizons use radioisotope thermoelectric generators, or RTGs. These devices convert heat from radioactive decay, typically plutonium-238, into electricity. They're reliable and long-lasting. The Voyager RTGs have been operating for nearly 50 years, but they're relatively weak, providing only hundreds of watts of power, and they decay over time. For more ambitious missions, we'd need more powerful solutions. Nuclear fission reactors, similar to those that power submarines and aircraft carriers, could provide kilowatts or megawatts of power for decades. NASA and other agencies have been developing small fission reactors specifically for space applications. Even better would be fusion reactors, which combine light elements like hydrogen isotopes to release energy, mimicking the processes that power stars. Fusion produces far more energy than fission, generates less radioactive waste, and uses fuel that's easier to obtain. But despite decades of research, we still haven't achieved sustained, practical fusion power on Earth. The challenges of containing plasma at temperatures hotter than the sun's core while extracting more energy than you put in have proven formidable. If we do crack fusion, though, it would revolutionize space travel. If fusion-powered spacecraft could generate enormous amounts of electricity for life support, propulsion, and scientific instruments, it could potentially even use fusion reactions for propulsion directly, expelling the hot plasma to generate thrust. Several theoretical designs for fusion-powered interstellar spacecraft exist, with names like Project Daedalus and Project Longshot, developed by physicists and engineers exploring what might be possible. Now, here's a thought that might surprise you. The hardest part of interstellar travel might not be the journey itself. It might be deciding whether to go in the first place. Consider this scenario. Humanity, in the year 2100, decides to launch a generation ship to Alpha Centauri. The journey will take 300 years with the best technology available. But technology improves over time. By the year 2200, someone invents a faster propulsion system that could make the journey in 150 years. Should we launch a second mission that would overtake the first? What do we tell the people on the first ship when the second one passes them halfway through their journey? This problem is sometimes called the weight calculation, or the incessant obsolescence postulate. If technology keeps improving, there might never be a best time to launch an interstellar mission, because waiting a bit longer always promises better technology and faster travel times. You could end up perpetually delaying because next year's spacecraft will be better than this year's. At some point, civilization has to make a decision. We're going now with what we have, accepting that future missions might surpass us. It's a strange psychological barrier, but it's a real one that mission planners will have to confront. There's also the question of what happens if we discover something revolutionary during the mission. Imagine a spacecraft halfway to Alpha Centauri when scientists back on Earth discover a wormhole or perfect warp drive technology. The slow boat to Alpha Centauri suddenly becomes obsolete, its crew committed to a journey that others can now complete instantaneously. How would the crew feel? Would they continue, or would they want to be rescued? These scenarios might sound like the plot of a science fiction novel, but they touch on real issues about commitment, progress, and the human relationship with time and technology. Let's shift to something more immediate and concrete. What are we doing right now to prepare for eventual interstellar travel? More than you might think, actually. The Voyager missions, though launched in the 1970s, continue to provide valuable data about the edge of our solar system and the beginning of interstellar space. Voyager 1 is currently over 15 billion miles from Earth, farther than any human-made object has ever traveled. The data it sends back about magnetic fields, particle densities, and the structure of the heliosphere, the bubble of solar wind surrounding our solar system, helps us understand what conditions are like in the space an interstellar craft would traverse. The Parker Solar Probe, which I've mentioned before, is doing something equally important from the opposite direction. By diving closer to the Sun than any previous spacecraft, skimming through the solar corona at speeds exceeding 400,000 miles per hour, it's testing materials and technologies in extreme conditions. The insights gained about thermal protection, high-speed navigation, and instrument survival inform the design of future spacecraft that might face similar challenges during interstellar acceleration or when approaching other stars. Meanwhile, the James Webb Space Telescope is revolutionizing our understanding of exoplanets. Launched in December 2021, this incredible observatory sits at a gravitational balance point 1 million miles from Earth, peering deeper into space and time than any telescope before it. Its infrared vision allows it to analyze the atmospheres of distant worlds, detecting molecules like water vapor, carbon dioxide, and potentially biosignatures that might indicate life. Every exoplanet JWST studies helps us build a catalog of destinations, a target list for future interstellar missions. We're learning which types of planets are common, which stars are most likely to harbor habitable worlds, which chemical signatures suggest active geology or biology. This reconnaissance work is essential preparation for the day when we can actually visit these distant shores. Ground-based efforts matter too. Projects like Breakthrough. Listen, a 10-year initiative to search for signs of intelligent life, scan the skies for radio and optical signals that might indicate technological civilizations. Even if we never detect anything, the effort advances our radio astronomy capabilities and keeps alive the possibility that we're not alone. And in laboratories around the world, scientists are tackling the fundamental physics and engineering challenges of interstellar travel. Researchers at NASA's Jet Propulsion Laboratory work on advanced propulsion concepts. Teams at universities study materials that could form ultra-thin light sails. Physicists explore whether quantum mechanics might offer loopholes in our current understanding of faster-than-light travel. All of this work, even if it doesn't directly result in an interstellar spacecraft tomorrow, builds the knowledge foundation we'll need when we're ready to take that leap. But here's something we need to confront honestly. Interstellar travel might reveal uncomfortable truths about our universe. What if we reach Alpha Centauri and find nothing of interest? Barren rocks orbiting in the void, no life, no resources worth the journey. What if the galaxy is mostly empty, with habitable worlds rare and widely separated? This possibility is deeply unsettling because it challenges the implicit hope underlying much of space exploration, that the universe is full of wonder, that there are countless worlds to discover, that somewhere out there we'll find life or intelligence or something that makes the journey worthwhile. The truth might be more austere. The universe might be mostly dead rocks and burning gas, with life so rare that even interstellar civilizations could search for millions of years without finding another. If that's the case, every living world becomes infinitely precious, and the responsibility to preserve Earth's biosphere becomes even more critical. On the other hand, what if we find too much life? What if every planet we visit harbors microbes or more complex organisms? That would be wonderful for biology, but potentially dangerous for us. We'd have to worry about contamination in both directions, protecting alien ecosystems from Earth organisms we might accidentally introduce, and protecting Earth from alien microbes that could potentially cause disease. This isn't just theoretical. NASA and other space agencies already have planetary protection protocols to prevent contamination of Mars and other bodies in our solar system. For interstellar missions, these protocols would need to be even more stringent. We'd essentially need to sterilize any spacecraft destined for landing on another world, ensuring we don't accidentally commit biological imperialism by introducing invasive species to pristine ecosystems. And then there's the most provocative scenario. What if we find intelligent life, not radio signals detected from thousands of light years away, but actual contact with another civilization, either by discovering their artifacts or by them discovering ours? First contact would be the most significant event in human history, period. It would fundamentally alter our understanding of our place in the cosmos, our uniqueness, our future possibilities. But it would also be fraught with danger and complexity. History shows us that when civilizations with significant technological disparities meet, the results are often tragic for the less advanced civilization. European colonization of the Americas, Africa, and the Pacific resulted in devastating loss of life and culture for indigenous peoples. Would we be the indigenous people in an interstellar contact scenario, or the colonizers? Or might both civilizations be roughly equal, leading to a more balanced exchange? Some scientists argue we should be cautious about broadcasting our presence to the galaxy, citing these historical precedents. Others contend that any civilization capable of interstellar travel would likely be advanced enough to have outgrown destructive tendencies. Otherwise, they would have destroyed themselves before achieving such technology. It's an unresolved debate with profound implications. If we do make contact, communication would be extraordinarily challenging. Not just the physics of sending signals across light years, but the fundamental problem of establishing mutual understanding with beings who might think in completely alien ways. We'd likely start with mathematics and physics, universal concepts that any technological civilization would understand. But conveying more complex ideas, philosophy, emotion, art, history, would require patience and creativity beyond anything humans have attempted. Perhaps the most important question is what we'd learn from such contact. Would an advanced civilization share knowledge that could help us solve our problems, clean energy, medical advances, perhaps even insights into consciousness and the nature of reality itself? Or would there be a prime directive-style prohibition against interfering with less developed civilizations? We can't know the answers, but the questions themselves reveal why interstellar exploration matters so much. It's not just about going to other stars, it's about understanding who we are, where we fit in the cosmic order, and what our future might hold. Let me share something personal here. When I look at the night sky, really look at it from somewhere dark enough to see the Milky Way stretching overhead, I feel something profound. It's humbling, certainly, to recognize that each of those points of light is a sun, possibly with planets, possibly with life, all unimaginably distant. But it's also uplifting. We are connected to those distant stars. The atoms in our bodies were forged in stellar furnaces, scattered across space by supernovae, and gathered by gravity into the planets and life forms we know. Carl Sagan famously said we are made of star stuff, and it's literally true. The iron in your blood, the calcium in your bones, the carbon that forms the backbone of every molecule in your body, all of it was created in stars and scattered when those stars died. You are the universe made conscious, matter arranged in such a way that it can contemplate its own existence and origins. Interstellar travel would be the universe exploring itself, consciousness reaching out to touch other manifestations of cosmic evolution. Whether we achieve it in 50 years or 5,000, whether we send robots or humans or digital consciousnesses we can barely imagine, the impulse is fundamentally the same. We are part of something larger, and we yearn to understand and connect with it. Now let's talk about something often overlooked, the economics of interstellar travel. Space exploration has always been expensive, but interstellar missions would operate on an entirely different scale. How do we pay for something that might cost trillions of dollars and yield returns only centuries later? Traditional economic models don't work well for interstellar exploration. Companies need profits within years or decades at most. Governments plan in election cycles, but interstellar missions demand thinking across centuries, investing resources with no expectation of immediate return. It's closer to the mindset that built medieval cathedrals, projects that took generations to complete, built by people who knew they'd never see the finished result. One possible model is international cooperation on an unprecedented scale. The International Space Station, despite its limitations, demonstrates that nations can collaborate on expensive, long-term space projects. An interstellar mission might require something similar, but much larger, a truly global effort where humanity pools resources toward a shared goal that transcends national boundaries. Some futurists propose that advanced artificial intelligence and automation might eventually make space exploration far cheaper. If self-replicating robots could mine asteroids, build solar panels, and construct spacecraft in orbit using raw materials from space rather than launching everything from Earth's gravity well, the economics change dramatically. What seems impossibly expensive with current launch costs might become feasible with mature space-based industry. There's also the possibility that the search for resources might eventually drive interstellar exploration. Our solar system contains enormous mineral wealth in asteroids and planets, enough to sustain civilization for millions of years. But other star systems have resources too, and some might have materials we can't find locally. If we develop the technology to extract and return valuable cargo from interstellar distances, admittedly an enormous if, there might eventually be an economic case for such missions. But I suspect the real driver won't be economics in the traditional sense. It will be the same drive that funds pure research, that builds telescopes and particle accelerators, that sends probes to Pluto and Saturn's moons. We do these things not because they make money, but because they expand human knowledge and capability. They're investments in our collective future, in the kind of civilization we want to become. Consider the Apollo program. The United States spent about $25 billion in 1960s money, equivalent to over $200 billion in today's dollars, to land humans on the moon. The economic return was difficult to quantify. We didn't mine lunar resources or establish profitable industries in space. But the technological spin-offs, the inspiration of generations of scientists and engineers, the demonstration that humans could accomplish something previously thought impossible, these intangible benefits shape the modern world in ways that can't be reduced to a balance sheet. Interstellar exploration would be Apollo multiplied by 1,000, a commitment across generations to push the boundaries of what's possible. The civilization that undertakes such a project would be making a statement about its values, declaring that some things matter more than quarterly profits or short-term political advantage. Let's examine what success might actually look like. Imagine we're in the year 2150. Humanity has launched multiple probe swarms toward nearby stars using advanced light sail technology. The first wave is approaching Proxima Centauri, ready to fly through the system at a fraction of light speed, gathering data and beaming it back to Earth. The probes send back the first close-up images of Proxima Centauri b, the potentially habitable planet discovered back in 2016. The world turns out to be tidally locked, always showing the same face to its star, just as our moon always shows the same face to Earth. One hemisphere bakes in eternal daylight while the other freezes in permanent night. But between these extremes lies a twilight zone, a ring of habitable climate where liquid water pools in vast seas. The probes detect oxygen and methane in the atmosphere, compelling evidence for biological activity. Lower altitude passes reveal patterns in the ocean surfaces, perhaps algal blooms, seasonal variations that suggest active ecosystems. On the twilight zone's landmasses, sensors detect complex organic chemistry, signatures that might indicate forests or their alien equivalents. Back on Earth, the images arrive 4.3 years after being transmitted. The reaction is electric. News outlets worldwide broadcast the alien landscapes. Scientists pore over the data, debating interpretations. Artists imagine what life might look like on a world where the sun never moves in the sky. And mission planners immediately begin designing follow-up missions, larger probes that can slow down, enter orbit, maybe even deploy landers to directly sample the environment. Humanity has found life beyond Earth. Not just microbial life, but possibly complex ecosystems, perhaps intelligence. Everything changes. The question is no longer, are we alone, but what are our neighbors like and how do we reach them? This scenario isn't wildly speculative. It's based on missions that could potentially be launched this century using technology that's currently being developed or is at least theoretically feasible. Whether it happens in 2150 or 2350 depends on choices we make now, how much we invest in research, how seriously we take space exploration, how well we manage global challenges that could derail our technological progress. But let's also consider a different scenario, one where we don't find life, at least not right away. The first interstellar probes visit several nearby stars and find planets, yes, but worlds that are barren, airless rocks or gas giants, offering no foothold for biology as we know it. The data is valuable scientifically, teaching us about planetary formation and stellar evolution, but there's no dramatic discovery of life. In this scenario, does humanity lose interest? Do we decide interstellar exploration isn't worth the cost if the payoff is just more lifeless rocks? Or does it strengthen our resolve, expanding our search to more distant stars, to older star systems where life might have had more time to develop, to unusual stellar environments we haven't yet considered? I think we'd continue searching. Because the question of whether we're alone is so fundamental to human identity that we won't stop asking until we have a definitive answer. And if that answer turns out to be that life is extraordinarily rare, that Earth is precious beyond measure as perhaps the only living world in our galactic neighborhood, that knowledge itself would be profound and worth having. There's another aspect of interstellar travel we should discuss: terraforming. If we reach another star and find planets that aren't quite habitable but could be made so, would we attempt to transform them into Earth-like worlds? Terraforming is the process of deliberately altering a planet's atmosphere, temperature, surface topography, or ecology to make it suitable for human habitation. It's a staple of science fiction, but also a serious subject of scientific study, particularly regarding Mars. Mars is cold and has an atmosphere too thin to breathe, but it's close enough to habitable that we could imagine transforming it over centuries. We might release greenhouse gases to warm the planet, melt the polar ice caps to create oceans, introduce microorganisms to begin building an oxygen-rich atmosphere. It would take hundreds or thousands of years, but it's not physically impossible. For exoplanets around other stars, terraforming would be even more challenging due to the difficulty of transporting materials and equipment across interstellar distances. But if we found a world that was close to habitable, maybe too cold, or with an atmosphere lacking oxygen but otherwise suitable, targeted interventions might be possible. The ethical questions around terraforming are immense. Do we have the right to alter an entire world to suit our needs? What if there's indigenous life, even just microbes? Does their existence take precedence over human colonization? These are questions without easy answers, debates that will likely rage for generations once we have the capability to make such choices. Some philosophers argue that we have a moral imperative to spread life throughout the universe, that a lifeless rock has no interests or rights to violate, and transforming it into a living world is an inherent good. Others contend that every world has intrinsic value in its natural state, that we shouldn't presume to remake entire planets in our image. These debates will become increasingly urgent if and when we develop interstellar capabilities. The decisions we make will define what kind of spacefaring civilization humanity becomes: cautious stewards respecting the universe as we find it, or bold transformers reshaping worlds to suit our vision. Let's talk about something that might seem tangential, but is actually central to the whole enterprise: why we should care about interstellar travel right now, in our lifetimes, even if we won't personally benefit from it. It's easy to dismiss interstellar exploration as a distant dream, something for our great-great-grandchildren to worry about while we focus on immediate concerns. But the groundwork we lay today determines whether those future generations will have the option of reaching the stars. Every investment in fundamental physics, every advance in materials science, every improvement in artificial intelligence and robotics, every mission we send to Mars or the outer solar system, all of these build the foundation for eventual interstellar capability. If we neglect space exploration now, if we allow our technological civilization to stagnate or regress, we push that future farther away or potentially make it impossible. There's also a more philosophical dimension. Working toward interstellar travel gives humanity a shared long-term goal, something that transcends the petty conflicts and short-term thinking that dominate so much of human affairs. It's aspirational in the best sense, a vision of what we could become if we choose cooperation over conflict, long-term thinking over immediate gratification. The late physicist Stephen Hawking argued that humanity needs to spread beyond Earth for our long-term survival. He wasn't being pessimistic about Earth's immediate prospects, but rather thinking on timescales of centuries and millennia. On those timescales, asteroid impacts, climate shifts, and countless other catastrophes become near certainties. Having human settlements on multiple worlds, ideally around multiple stars, provides insurance against any single catastrophe ending our species. This isn't about abandoning Earth. It's about ensuring that the light of consciousness and culture that has evolved here over billions of years doesn't blink out. Every species that has ever existed on Earth is either extinct or will eventually be. But humans have the unique capability to potentially transcend that fate by spreading beyond our planet of origin. Some critics argue that we should fix Earth's problems before thinking about space. But this presents a false choice. We can work on climate change, poverty, disease, and social justice while also advancing space exploration. In fact, many technologies developed for space have direct applications to Earth's challenges: satellite monitoring of climate and agriculture, water purification systems, energy efficiency innovations, materials that withstand extreme conditions. Moreover, the perspective shift that comes from seeing Earth from space, the famous overview effect that astronauts describe, tends to strengthen environmental awareness and sense of global unity. Astronauts report that borders disappear from orbit, that Earth looks like a fragile oasis in the vast darkness, that the atmosphere appears terrifyingly thin. This perspective has created some of the strongest advocates for protecting our planet. Interstellar exploration would extend that perspective even further. Seeing Earth not just from orbit but from another star system, a pale blue dot billions of miles away, would emphasize just how special and rare our world is. Even if we find other habitable planets, Earth would remain our home, the world that gave birth to human civilization, worthy of protection and reverence. Let me address a question you might be thinking. Is all this talk about interstellar travel just escapism? Are we dreaming about distant stars to avoid dealing with problems here and now? I don't think so. Throughout history, the civilizations that thrived were those that balanced practical concerns with aspirational goals. Ancient Greeks dealt with political conflicts and economic challenges while also making fundamental advances in mathematics, philosophy, and astronomy. The Islamic Golden Age saw incredible cultural flourishing despite political turbulence. The Renaissance transformed Europe even as plague and war ravaged the continent. Having grand visions, whether building cathedrals, composing symphonies, or reaching for the stars, doesn't prevent societies from addressing immediate needs. Often it provides the motivation and framework that makes solving practical problems more achievable. A civilization that thinks only about the next quarter's profits or the next election cycle tends toward short-sighted decisions that create long-term problems. Interstellar exploration represents perhaps the ultimate long-term goal, something that requires sustained effort across multiple generations. Working toward it forces us to think about the kind of world we're leaving to future generations, the values we want to perpetuate, the knowledge and capabilities we want to preserve and expand. Now, as we approach the end of this exploration, let me paint one more vision of what could be. It's speculative, aspirational, but grounded in possibilities that don't violate known physics. The year is 2500. Humanity has become a true spacefaring civilization with settlements throughout our solar system. Millions live on Mars in rotating habitats orbiting Earth, on the moons of Jupiter and Saturn. Automated systems mine asteroids and process materials in zero gravity, building structures that would collapse under Earth's gravity. And in Earth orbit, construction has just completed on the first crewed interstellar vessel. It's enormous, a cylinder 5 miles long and half a mile in diameter, spinning to create artificial gravity. Inside are ecosystems, forests, lakes, agricultural zones that will sustain 10,000 people for the 500-year journey to Tau Ceti, a sun-like star 12 light-years away, where probes have confirmed 3 potentially habitable planets. The ship's propulsion system combines several technologies: nuclear fusion engines for steady acceleration, a massive light sail that will catch laser beams from solar system arrays to boost speed, and advanced ion drives for maneuvering. It will eventually reach 15% of light speed, making the journey in about 80 years of external time, though the crew experiences it as the full 500 years across multiple generations. The Voyagers know they'll never see Earth again. Communication will continue, but the time lag will stretch to decades as they travel farther. They're not fleeing Earth or humanity, they're extending it, carrying the seeds of human civilization to another star. Before departure, there are ceremonies broadcast across the solar system. Historians place time capsules aboard containing art, literature, music, scientific knowledge, the achievements of human civilization preserved for whatever they might encounter. Religious leaders of various faiths bless the mission. Children who will grow up, grow old, and die aboard the ship wave goodbye to a home world they'll never see again. And then they leave, a single spark of life and consciousness, venturing into the cosmic darkness, carrying hope that on a distant shore humanity will plant new roots and look up at unfamiliar stars, continuing the ancient human tradition of asking what lies beyond that horizon. This vision might seem fantastical, but it's built on extrapolations of current technology and current understanding of physics. Nothing in it requires warp drives or wormholes or physics we haven't discovered. It requires enormous resources, sustained commitment, and continued technological progress, but those are challenges of will and organization rather than fundamental impossibility. Whether this specific scenario unfolds or something completely different emerges, the underlying truth remains. If humanity survives and thrives, if we continue our technological and social evolution, we will eventually reach for other stars. It's what we do. We explore, we expand, we push boundaries. It's woven into our DNA from millions of years of ancestors who looked beyond the next hill, crossed the next valley, sailed beyond the horizon. But how long would it take to reach each planet in our solar system? Check out the video at the left side of the screen. In this video, we break down the real travel times to Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto using current rocket technology, gravity assists, and even future propulsion concepts like nuclear, ion, and fusion rockets. See you there.